Hi, I'm Sebastian Mate, and in this video I will give you an introduction to Magic Quartz, a solution for precise turntable speed control for turntables with AC motor. So in this video we will have a close look at the software features. We will discuss what Magic Quartz is actually good for and have a look at some measurements. We will also have a closer look at the open source part of the project, and finally I will show you how you can flash the firmware onto a standard Arduino development board. This is really a great thing because it allows you to test Magic Quartz without a turntable speedbox. So let's get straight into it. Before we go down the rabbit hole, I need to mention a few basic things. The whole project is split into two parts. Magic Quartz, the first part, is the software. It is highly configurable and can be used for control and signal generation in true sine inverters. It is proprietary because I want to keep the possibility open to commercialize it one day. For now, however, it is available completely free of charge. Please check my homepage for details. The second part covers the hardware. This is what I call the Magic Quartz tech demo. It is an open source implementation of a turntable speedbox capable of running the Magic Quartz firmware. It was designed for ease of replicability and it uses mostly off-the-shelf components. You can use the tech demo to virtually explore the device and to 3D print a physical enclosure. There's also an electronic design for a main board. Here's a typical application for Magic Quartz. The firmware can be used to drive a turntable speedbox, such as the previously mentioned tech demo. Such a speedbox could be powered with a low DC voltage, and usually an inverter is integrated into the speedbox to generate the AC for the record player. The frequency of the AC is variable and it is used to control the speed of the turntable. There's also the possibility to measure and automatically regulate the speed of the record player. This can be done, for example, via an optical motion sensor next to the record player's bladder. So now let's have a closer look at the software features. For this I have connected the speedbox to my Dual 1219 turntable, which uses a synchronous AC motor. I have also connected a small oscilloscope so that I can show you what the speedbox does with the AC when I change the settings on it. And we're in the main menu. Please excuse the flickering of the voltmeter in this video. This is because its display is multiplexed. In reality, it looks very steady. Magic Quartz is cursor controlled. You can use the left and right buttons to move the cursor on the screen, and then use the up and down buttons to enter or leave functions or to increase or decrease values. In this way, you can, for example, change the frequency of the generated AC. As you can see, this also changes the RPM in the upper line of the display. And of course, this also works the other way around. So this allows you to precisely adjust the speed of the turntable. However, it is cumbersome to enter all digits in case you want to switch between standard record speeds. For this there is a shortcut. If you move the cursor below RPM in the upper right corner, you can switch between the standard record speeds. 33, 45 and 78 RPM. And yes, we also have 16 RPM. Now let's have a quick look at the hardware side. It is good to know that Magic Quartz is not directly switching between frequencies, instead it's ramping between them. For example, if I switch between 33 and 45 RPM, it looks like this. Now this is 78 RPM and we're up at 117 Hz. And in the other direction it looks like this. We can also go down to 16 RPM, which is 25 Hz. Another important feature of Magic Quartz is its capability of measuring the inverter current. So this is primarily a safety feature, as it allows Magic Quartz to detect and intercept potential hardware faults. It is also used to detect whether the turntable motor is on or off, and it is used to correct the generated voltage. I call this feature Advanced Power Management, or APM for short. As you can see, whenever I switch the turntable motor on, a flash symbol appears in the lower right corner. You can also see that the speedbox maintains a very stable 220 volts. For musicians, there is an additional nice feature. If you move the cursor below the T symbol, you can change the pitch in semitones. So the basic idea behind Magic Quartz is to convert between RPM and frequency. However, for this to work, the software needs an additional piece of information. It is what I call the physical turntable speed. Well, this is the record speed that the turntable is currently set to. This record player, for example, has 3 record speeds. And this is reflected by the setting in the upper left corner. For example, if I change the turntable to 45 RPM, I must also change this setting to 45. From now on, all speed calculations will be based on 45 RPM. Now, when I convert the speed to 33 RPM, you can see that the speedbox is now generating 37 Hz to achieve the 33 RPM playback speed. Now, let's have a look at Magic Quartz's most exciting feature, the so-called Live Quartz mode, where the speedbox continuously monitors and adjusts the playback speed. This mode can be accessed from the main screen by selecting the Q symbol. Of course, the turntable needs to be switched on for this to work. Magic Quartz then performs a quick calibration of the optical sensor and then enters Live Quartz mode. As you can see, in my case, it has also reduced the voltage down to 120 volts, which reduces the motor hum. This is an additional feature that can be used with synchronous turntable motors. The screen in Live Quartz mode is very similar to the one in the main menu, except that everything happens automatically. The upper line shows the currently measured turntable speed and the lower line the currently generated AC frequency. In the lower left corner there is a rotation indicator that progresses to the next rectangle upon each rotation of the turntable platter. This is very useful to see if the optical motion sensor is working as expected. In the lower right corner, Magic Quartz displays some icons that indicate whether the speedbox is increasing or decreasing the frequency. The part in the upper left corner displays the status of a ring buffer that is used to calculate the average speed of the turntable. You can read about this in the manual. So the implementation of the speed control is actually quite clever, as it can handle speed deviations and measurement errors quite efficiently. For example, smaller speed deviations are automatically cancelled out due to the inherent design of the speed control algorithm. However, if larger speed deviations occur, for example when the turntable's automatic start and stop functions kick in, Magic Quartz is also able to detect this and discard the measurements. I can show this to you by activating the stop function of my turntable. Magic Quartz immediately detects this and restores the nominal voltage. It also rejects the speed measurements and pauses the regulation. And finally, it has also detected that the turntable has been switched off. Let's exit this for now. So these were the core functions of Magic Quartz that you would use when listening to music. In this context, I would like to mention that Magic Quartz remembers the last mode it was in and continues with it the next time you turn the device on. The software was really designed to let you focus on your music and not on Magic Quartz. But there is much more. In the lower left corner, there's an M symbol which takes you to a configuration menu with more than 40 additional functions and configuration parameters that you can use to tailor the speedbox to your needs or preferences. There's really a lot that you can do, and showing everything would be beyond the scope of this video. If you are interested in tweaking the settings or configuring Magic Quartz for another turntable, please leave it down in the comments and I will see if I can make another video about that. Let's have a look at some data and why you may want to use Magic Quartz. Note that for the following I have created a modified version of Magic Quartz that can log its data to a computer. You can find this firmware on my website in case you want to replicate my experiments. A problem with record players with AC motor is that their speed is tied to the mains AC frequency, and this is not very precise. For example, let's have a look at a frequency chart of the European electrical grid in July. This was taken in the evening and covers an hour. During this time, I had connected my turntable to the mains and used the modified Magic Quartz firmware to log the speed. It's not surprising that the speed of the record player correlates perfectly with the electrical grid's AC frequency. Here you can see both graphs combined. Now you will ask, can you hear this? Well, no. These speed deviations are very small, but as you can see, they can be measured. And the problem can be overcome easily by using a stable frequency source, such as Magic Quartz. Because Magic Quartz generates the AC frequency on its own, it would isolate the record player from such fluctuations. Another problem that Magic Quartz tackles are slow speed drifts, and there are two major sources according to my research. One is speed deviations due to needle friction. Here you can see a record played back on both sides. You can also see that the speed increases on each side. This is because the needle causes more friction on the outer part of the groove compared to the inner part. Note that for this I had disabled the speed regulation in Magic Quartz. This was recorded with the turntable at exactly 50 Hz. And of course this can be compensated with the speed regulation turned back on. The second source for speed drifts are lubricants warming up. This is a different turntable, a Dual 1019, which probably needs a major overhaul. You can see that its speed increases over the record dramatically, and this is really big. Notice the scale on the left. And of course, even this can be compensated in Magic Quartz. Now let's have a quick look at the open source part of the project, the Magic Quartz tech demo. I made everything available on GitHub, and I will provide a link to this in the video description below. So this repository basically comprises two parts. First, there's an OpenSCAD model that can be used for 3D printing a physical enclosure, but it can also be used for virtually exploring the device on your computer, and we will do this in a moment. Second, there's a KiCad design for a mainboard, and this comprises a schematic and a PCB, and we will have a look at this as well. Then there is some information regarding the licensing and a disclaimer and some safety considerations. Please be sure to read these sections very carefully, and please be aware that building one of these devices is not for beginners. You must absolutely understand what you're doing when you attempt to build one of these. Then there's some information regarding the 3D model and some 3D printing tips. A section that describes which components should be used. And there we have a section regarding the electronic design. For example, a screenshot of the schematic, the PCB, and a brief description of the circuit. A block diagram. And this is important. There's also a section called known issues, which is updated regularly. You should check back from time to time to see if there are any updates. Then we have some parts lists, assembly notes, and the basic steps which describe the initialization procedure. Basically, this is what you have to do when you turn the device on the first time. Now, basically, you can navigate the whole project structure directly here on GitHub, but it's easier if you download everything onto your computer. And this can be done easily by clicking on the code button and then on download zip. I have already downloaded the files to my computer. Now let's have a quick look at the OpenSCAD model. To open the file, go to Source, OpenSCAD, and open this file. It should look like this. With this file you can do different things. First, of course, you can have a close look at the device on your computer, but you can also use this to generate the 3D printable parts. So this is described in the documentation on the GitHub site, but I will show you briefly what to do. So the first thing that you generally do is to remove the cover, because we don't need that. And now we also remove all components. Now we have the bare enclosure, and we can generate the distinct parts by changing this variable to the respective part number. For example, if we set it to 1, it generates the bottom plate. Or we can also generate the cover. If we change this to 5, it looks like this. And you can easily export these to STL from OpenSCAD, but for your convenience I have already done this, and you can find these files in the release folder STL, and there you have them. Then there is the electronic design of the mainboard. You can find everything under Source, KiCad, Magic Quartz Mega. In this folder, simply open the file KiCad Pro in KiCad, and from there on you have access to the schematic and PCB. Now, the PCB has been designed as a single-sided board, and therefore it can be fabricated easily. For example, if you have a small CNC machine. However, it's easiest if you get it made by one of the popular PCB manufacturers. This is easy and very cheap. For this, you would have to export the Gerber and Exelon files from the PCB layout in KiCad. Again, for your convenience, I've made these files already available in the release folder. Simply go to Gerber. And to have the PCB manufactured, you typically would have to zip these files first before you can upload them on the PCB manufacturer's website. Now let me show you how you can flash the Magic Quartz firmware onto a standard Arduino development board. This is really a great way to try out the firmware without having to build a turntable speedbox in advance. And if you're into electronics, the chances are pretty good that you already have one of these lying around at home. In fact, you do not need anything more than this Arduino board, because you can interact with the firmware via the serial communication over your computer, and we will do this in a moment. However, if you have one of these lying around at home, this is a standard LCD keypad shield, you can also use this with the firmware. Simply connect both components together, and you have a very nice device which you can use for prototyping a turntable speedbox. Just make sure that the USB socket does not short out the pins of the upper PCB when you connect both together. However, if you're planning to build the Magic Quartz tech demo, you would have to use this. This is a Mega 2560 Pro board, which obviously uses a much smaller footprint and can therefore be integrated easily into custom hardware designs. And this is also the reason why I chose it for the tech demo. Note that it also uses a real quartz crystal, which provides superior timing accuracy compared to the resonators on the normal Arduino boards. So what I will do now is I will connect the bare Arduino board to my computer, and then I will show you how you can flash the firmware onto it. Okay, now I have connected the Arduino board to my computer and already opened the Arduino IDE. Before I will flash the Magic Quartz firmware, I would like to briefly test whether the Arduino board works as expected. And this can be done easily via the so-called Blink program. This can be found under Files, Examples, Basics, Blink. There simply click on the Upload button and it will upload the Blink program. If flashing the Blink program was successful, the Arduino's LED should blink in 1 second intervals. Unfortunately, uploading the Magic Quartz firmware is more complicated because there's no easy way to use the Arduino IDE directly to upload the hex file, but we can use a trick to achieve this. So to do this, we first go into the settings under File, Preferences, and then we tick Show verbose output during upload, and then we upload the Blink program once more. Now you can see that there's much more debugging output in the lower part of the window, and the interesting part that we are interested in is the third line, which is the command line parameters for AVRDUTE, which is the program that actually uploads the firmware to the Arduino board. And we can copy this and paste it into a text editor. Now all we have to do is to replace the file. So we replace this with Magic Quartz. Hex, and then we can upload the firmware. But before we do this, we have to close the Arduino program first. And then we copy and paste the command line. And then we can flash the firmware. There's a very simple test to see if the firmware has been uploaded successfully. Whenever you connect the board to USB power, or if you press the reset button, the LED will flash for 1 second very fast. See? If I press the reset button, it will flash again. This indicates that it's running the Magic Quartz firmware. Of course, if you happen to have a LCD keypad shield, verifying the upload is very easy. Please note that on some Arduino boards it may take longer to start the firmware. This is especially the case if you have the Arduino development IDE running on your computer. So as you can see, it has started into motor setup, and we will do this in a moment, but we will do this on the computer by using a third way to verify the upload, which is the serial connection. And this can be done easily. To connect to the Magic Quartz firmware using the serial communication, you can use the Screen program. Now, if you do not get any output here, you may have to press the reset button on the Arduino board. As you can see, it's now starting up again, and we're again in the motor setup. I won't go into any detail here. You can read about this in the documentation. So I will go briefly through this so that I can show you the main screen. Now, at first, it's asking me to set the default frequency, which I will keep at 50. Then I will set the waveform to 2. The phase shift I will keep at 0. Now it's asking me to turn on the motor and to adjust the voltage. Of course, I have nothing connected yet to this Arduino board, but I can set this to 1 to generate the maximum amplitude of the signal being generated. And that's it. Now we're in the main menu, and as you can see, you can basically do everything as you can do with the real speed box. You can adjust the speed. You can also use the speedbox function in the upper right corner. And you can also use, of course, the configuration menu with almost all functions. Almost means there's one limitation, because the Arduino board does not implement the advanced power management. There are some functions that are not usable, for example, this power info function. Also notice that when running on the Arduino board, it assumes that the motor is always switched on. Therefore, it's showing this R symbol in the lower right corner. But otherwise, you can use this to connect peripherals, such as the LCD screen, the buttons, or even an inverter to the Arduino board, and then you can start building your own Magic Quartz-based turntable speedbox. So that's it for this video. I really hope you liked it. If you did, please give it a thumbs up and consider subscribing to my channel. Of course, I'm very interested in your feedback, so if you have any questions or remarks, please feel free to comment down below the video. I will close this video with some additional footage showing the speed regulation in Magic Quartz after it has stabilized. But for now, see you next time. Bye.